And so what is it going to take to get there? How are we going to build ourselves a fault-tolerant quantum computer, and what is needed to arrive there, and where are we today? So today, I'll give the example for superconducting qubits. It's one of the most common architectures and modalities for quantum computing, and then where we believe we need to be in the realm of useful quantum computing, where there is application expectations of immense benefit. So today, we are at or a little bit below one logical qubit. A logical qubit is a qubit that has a very low error rate. You can force it to be as small as you wish if you invest enough overhead in the error protection and error correction itself. It's really easy then to model this. So when you look at these algorithms from Shor's algorithms or Grover search, they are modeling fault-tolerant qubits, perfect qubits, you could say. So there's been a number of demonstrations by Google and IonQ and QEra that we're at this realm of really approaching or near a fault-tolerant 1 qubit, right? But then you likely need 10,000s to hundreds of thousands of these to really realize these large applications around chemistry and optimization. And what is a logical qubit composed of? It's composed of physical qubits, the actual qubit that's been written there or is in the lab. Today, we're on the order of 400 to 500 for superconducting as the max number, 1,000 roughly for neutral atoms, which actually are shuttled around. And so we're making progress. I'll show a chart about the development, but still a long ways to go to get to roughly 1 million physical qubits, which we believe with that overhead of about 100 or 1,000 of error correction. Because to protect a qubit and make a logical qubit, you have to actually use more qubits and use a surface code or other types of codes to protect that data, detect errors and correct them without copying or making measurements of the data qubits. So you have data qubits and you have measured qubits, and you entangle them, and then you track the measured qubits and see if there's been a change in parity, which means that you've had likely an error in the data qubit that you then can correct. But one of the powers and challenges of quantum computing is that you can't copy a qubit without destroying the state. So you have to set up these T factories and other ways to protect the qubits. So we have a ways to go. We've made great progress, but there's still a ways to go. On the error rate side, great progress on increasing the fidelity, reducing the error rate, but still a road to travel there. Superconducting qubits have on the order of 1 times 10 to the minus 3 or a little bit better of those 2 qubit error rates, but you need to be likely 1 times 10 to the minus 6 or better to actually do error correction at a large scale. And that's because the higher the error rate, the more work it is, the more overhead to protect that qubit. And the higher the fidelity, the lower the error rate, it's much easier to protect that qubit, less overhead. And so you want to have the highest fidelity that you can. But one of the challenges of quantum computing is that you need to both protect the qubit and increase the coherence time, but you also need to then make it entangled with other qubits and be able to read out that qubit. So this is tension of isolation and coupling so that you can use it in computation, but also protect it. And that's the game, really, of how do you protect it and keep the fidelity high, but then still be able to couple to it. And then finally, on error mitigation, great progress, a number of good developments the last few years around mitigating the errors. So reducing the impact of errors, reducing the error rate itself. There's a number of different techniques. There's better ways to calibrate a quantum computer. So there's a kind of a stock basic calibration of a quantum computer, but then depending on the gates used, the gate sequence that's part of an algorithm, then you actually want to make adjustments because there's gate bleeding, there's coupling, etc. And so actually tuning the calibration to be a specific algorithm or gate sequence is really powerful. And that's a technique that we're seeing used today. But to get to a fault-tolerant quantum computer, you're going to need to have error correction as well. So mitigation, so reduce those errors, minimize them as much as possible, and deal with what's left over, which hopefully is very small, with error correction. And so immense progress has been made in the last 10 years, but there's still a ways to go to get to that high-powered, useful quantum computer that likely needs to be fault-tolerant. And to do that, we'll need to then be able to do error correction.